Well, welcome everyone. I'm Dawn Marshall. I'm the director of the Safer Sin University Transportation Center. Safer Sin focuses on automated vehicle technology, connected vehicles, vulnerable road users, roadway infrastructure, and distributed simulation technology. Today we have a presentation from Dr. Yina Wu, who is a postdoc associate at the University of Central Florida. She'll be presenting on connected vehicles transition and market presentation. This research project focuses on connected vehicle crash warning systems that have the potential to improve vehicle safety by assisting drivers in their awareness of imminent situations. So Yina, if you'd like to take over, welcome and thank you for being with us today.
Thank you, Don. Okay. Hello, everyone. Thank you for attending the webinar. The project I'm going to introduce today is the impact of connected vehicle market penetration and connectivity level on traffic safety in connected vehicle transition period. I'm Yina from University of Central Florida. The project I'm going to introduce today include two parts. The first part include a driving simulator study, and the second part include a macro simulation study. So now let's look at the driving simulator study first. This study provides a driving simulator study to evaluate the effectiveness of head-up display warning system and audio warning system on driver's crash avoidance performance when the lead vehicle makes an emergency stop under fog condition. Upon arriving at the lab, each participant was briefly introduced to the requirement of the experiment, and all participants were required to read and sign a consent form. Before the formal experiments, participants had at least 10 minutes to get trained and familiarize themselves with the operation of the driving simulator. Then they performed the formal driving experiments under either moderate or dense fog with three different warning conditions in a random order. The three warning conditions include no warning condition, HUD only condition, and HUD with audio warning condition. Gender of the participants were also carefully considered when assigning the fog levels. Between each trial, participants could have at least 5 minutes to rest. After the experiment, the participants were required to finish a survey about their experience with the scenarios. More than 90% of the participants thought the driving simulator had a high level of realism. The picture shows in the slide shows the driving simulator that's in the UCF. 54 participants were recruited for this study. The average age of the participant was about 38 years old, ranging from 18 to 75 years old. Each participant should have a valid driver license and had at least 1 year of driving experience. Although 54 participants were recruited in this experiment, only the data of 48 participants were collected for the analysis, since 6 participants could not finish the experiment due to motion sickness. In the completed 144 trials, 7 trials were excluded because some participants chose to steering wheel to avoid hitting the lead vehicle, and some participants drove too slow and were not able to follow the front vehicle. So a dataset containing information for 137 trials were created for the analysis. During the experiment, the participant resumed driving on the outer lane of a 2-lane straight roadway segment under clear conditions. A lead vehicle was placed in front of the test vehicle with a speed of 50 miles per hour. The 50 mile per hour speed is driver's average speed under fog condition based on our previous driving simulator study. The drivers were asked to drive from a clear condition to a fog condition and not overtake the lead vehicle. Drivers follow the lead vehicle for about 1 mile in fog so that they should get familiar with the fog environment and adapt their driving behavior accordingly. Then a risky scenario was introduced in order to test the participants' performance under the dangerous condition, which is the lead vehicle was triggered to make an emergency stop with a high deceleration rate. This slide shows the experimental design of the driving simulator experiment. The experiment was a mixed factorial design with warning type as the within subject variable, age as well as fog as the between subject variables. As it was mentioned, there are three types of warning strategies during the experiment. No warning strategy, HUD warning only, HUD with audio warning. Two types of visibility conditions were included, which are the moderate fog and dense fog. The pictures in the slides show the visibility condition for the moderate fog and dense fog scenarios during the experiment. The visibility distance in the moderate fog condition is 300 feet, and the visibility distance for the dense fog condition were 100 feet. During the experiment, after the driver noticed the event, both throttle releasing behavior and braking behaviors will be taken. This figure shows an example of a typical stopping behavior. Driver will use the brake pedal after release the throttle. The points in the figure are the dependent variables for the throttle release analysis and braking analysis. Based on the key time moments shown in the figure, some critical measurements were defined and extracted to evaluate the participants' driving performance, which include time to initial throttle release, time to final throttle release, time to initial brake, time to 25% of brake, time to 50% of brake, time to 75% of brake, and time to maximum brake. Two MANOVA analyses were conducted for throttle release analysis and brake analysis, while ANOVA analysis was conducted for other dependent variables. So now let's look at the driving simulator experiment results. The first variable is the throttle release time. Three measurements were employed to assess the participant throttle release time, including time to initial throttle release, time to final throttle release, and time to initial brake. The repeat measure MANOVA analysis suggests that the warning type had significant effect on driver's throttle release time. However, no significant effect of different fog level, age group, and gender could be observed in terms of throttle release time. The ANOVA analysis results indicate that the time to initial throttle release and the time to final throttle release contribute to the multivariate effect. As it is shown in the table, post-hoc test suggests that participants under no warning condition need more time to start and finish the throttle release behavior. Since drivers could know the hazard event earlier with the warning system, they could take earlier reactions to avoid the potential collisions. However, there was no significant difference between HUD-only warning condition and HUD with audio warning condition, which indicate that adding audio warning system could not significantly affect participants' awareness of upcoming situation and hence could not shorten the throttle release time. The second variable is the brake time. Participants' brake transition time was examined by 4 measurements, which include time to 25% of brake, time to 50% of brake, time to 75% of brake, and time to maximum brake. The MANOVA test shows a significant effect of warning type and age. However, there was no significant difference between moderate and dense fog condition in terms of brake transition time. The repeat measure ANOVA analysis showed that warning type has significant main effect on both time to 75% of brake and time to maximum brake. As it is shown in the table, the post-hoc test indicate that the time to 75% of brake and time to maximum brake become longer under no warning condition compared with the HUD with audio warning condition. No significant difference could be observed between the two different warning types. In addition, the ANOVA analysis result of age shows significant impact on time to 75% of break and time to maximum break. The post-hoc test suggests that young drivers tend to spend longer time to reach 75% and maximum pedal pressure compared with working age and old drivers. However, no significant difference was found between working age and old drivers. The third variable is reaction time. The effect of warning type and age were found to have significant impact on reaction time. However, fork level and gender did not have significant impact on brake reaction time. From the result, there was significant difference of reaction time between no warning condition and HUD condition, which is shown in the left figure of the slides. Compared with no warning condition, HUD with audio warning condition has less reaction time. It was also useful to know that no significant difference could be observed between HUD only condition and the other two conditions. Regarding the effect of age, as it is shown in the right figure, the brake reaction time was the largest in the old age group, which indicate that old drivers need more time to respond to emergency events. However, the differences between young driver and working age driver was not significant. The next variable is the minimum modified time to collision. The minimum time to collision is an essential surrogate measure to evaluate rear end crash risk under full condition. Traditionally, only speeds were considered to calculate the time to collision, which leads to the assumption that a collision will happen only if the speed of the following vehicle is greater than that of the lead vehicle. Such an assumption would ignore a lot of potential conflict. Thus, this study utilized modified TTC considering both the speed and the acceleration or deceleration as was suggested by previous studies. The ANOVA analysis suggests that the effect of warning type and fork level had significant impact on the minimum modified time to collision, while the effect of gender and age is not significant. The post-hoc analysis indicates that minimum modified time to collision under no warning condition was significantly lower than that under HUD only condition, which is shown in the left figure. Although the no warning condition also had a lower minimum time to collision compared with HUD with audio warning condition, the difference was not significant, which could be caused by random effect. With the warning system, driver could become better prepared to avoid a potential conflict. Meanwhile, no significant difference could be observed between the two warning types. The right figure suggests that old driver could have significant larger minimum time to collision than working age driver, although the difference between the old driver and young driver is not significant. Young drivers tend to have smaller minimum time to collision compared to old driver. The last variable is the maximum brake pedal pressure. The ANOVA analysis shows significant effect of fork level and age on the maximum brake pedal pressure. However, warning type and age did not significantly affect maximum brake pedal pressure. The result of warning type indicate that the warning message will not affect participants' employment of maximum brake pedal pressure if the participant had realized the risky situation through either seeing the brake light of the lead vehicle or noticing by the warning message. The left figure in the slides indicate that driver would employ a larger brake pedal pressure under dense fork conditions compared with moderate fork condition. The right figure shows the effect of age. Old driver tend to shows the effect of age. Old drivers tend to have larger maximum brake pedal pressure compared with the other two age group, and there is no significant difference of brake pedal pressure between young driver and working age driver. So this table shows the summary of the experiment result. As it is shown in the table, participant throttle release time is only affected by the warning type, while participant brake transition time could be affected by both warning type and age. As for the response time, it could be affected by warning type and participant's age. In addition, minimum modified time to collision is affected by warning type and fork level, while maximum brake pedal pressure could be affected by both fork level and age. In this study, both the start moment of warning message and the moment when participants see the brake light of the lead vehicle could be regarded as stimulus, and the response to the stimulus of each driver under emergency situation is relatively similar. No significant difference was identified in participant throttle release time, brake transition time, or other performance measurement between HUD only and HUD with audio warning in this study. This phenomenon is possibly due to the fact that drivers are prone to be more carefully when driving under fog condition, and the audio warning was found to have safety benefit when drivers are distracted. In this study, no significant effect of fork level was observed for the participant throttle release time, brake transition time, response time, while participants would press brake pedal harder in dense fog. However, larger maximum brake pedal pressure was found under dense fog condition, which indicate that drivers have to select larger deceleration rate to avoid hitting the front vehicle. When fog became dense, participants in the test vehicle could not see the brake light of the lead vehicle, resulting in higher rear end crash risk. Also, old participants had significant longer brake reaction time because they need more time to make mental calculation. In addition, young participants spend longer time to reach 75% of brake and maximum brake force, which means their braking process could be smoother than other participants. Also, since all drivers start to brake relatively late, they were more sensitive to the potential risk, they could have smaller time to collision value by making harder brake. To conclude, the driving simulator experiment result indicates the positive effect of crash warning system on safety. It was found that the warning system can significantly reduce drivers' brake response time and minimum modified time to collision. Nevertheless, no significant additional effect of audio warning could be found. Also, the decrease of visibility distance could increase crash risk. Also, old drivers are more vulnerable road users under fog condition. And the second part of this project includes a micro-simulation experiment. The simulation experiment was conducted based on VISSIM to test an integrated variable speed limit and connected vehicle control strategies with a freeway section in Florida, where severe fog-related crashes have happened. The first figure shows the feasibility of utilizing the variable speed limit and connect vehicle control strategy to proactively improve traffic safety for a bottleneck area on freeway during fog. The study area has 3 lanes in each direction and a speed limit of 70 miles per hour. There are 6 lanes virtually implemented on the roadway, which is shown in the figure. A typical freeway bottleneck caused by a severe crash was selected for the simulation. The crash occurred between detector number 1 and detector number 2. After the crash happened, MVDS and the corresponding weather data were collected from fog monitoring system installed at the roadside. The fog monitoring system could provide weather data such as temperature, rainfall, and visibility distance. At the upstream of the crash location, 3 VSLs are implemented at detector number 3, detector number 4, and detector number 6. The in-field traffic data under heavy fog condition from 6:15 a.m. to 8:15 a.m. on February 2, 2016, with visibility distance between 45 meter and 88 meter, were collected for the model calibration to represent traffic condition during fog. After excluding 30 minutes of VISSIM warming up time and 30 minutes of cooling down time, the VISSIM data of 60 minutes were used for calibration and validation. The simulation network was calibrated by traffic volume at 15 minutes intervals and was validated by average speed at 15 minutes interval. GEH value was calculated by traffic volume from both field detector and simulation at 15 minutes interval. The calibration and validation result shows that the simulation scenario could well represent the real-world traffic. The scenario including vehicle without any control strategy was firstly simulated. Then the scenarios with variable speed limit and connected vehicle control strategies was developed in the simulation. The variable speed limit algorithm was fulfilled by the component objective model interface, which is used to program and regulate vehicles' movement. So this slide shows the proposed VSL strategy. We assume that the lead vehicle suddenly decreases its speed under fog condition. The relationship between gap and visibility distance can have two possible situations. If the gap is smaller than the visibility distance, the rear end crash occurrence situation would be similar to clear condition. However, there are two different situations if the gap is greater or equal to visibility. The first situation is when the following vehicle is able to see the front vehicle. The front vehicle speed has been decreased to the following vehicle speed has been decreased to the front vehicle speed. The second situation is when the following vehicle is able to see the front vehicle. The following vehicle is still decreasing its speed. Similarly, rear-end crash could happen if the high-speed traffic meets the low-speed traffic. Thus, a VSL strategy for fog condition could be proposed based on the above-mentioned analysis for different situations. The VSL strategies also include other constraints. For travel time, maximum difference between the post speed of the neighboring detectors and two consecutive time steps, as it is shown in the slides. This simulation experiment also considered connected vehicles. With the development of vehicle-to-vehicle technologies, drivers are able to communicate with nearby vehicles as the vehicle are able to send or receive information to or from other vehicles. With the V2V communication, driver could know the driving environment, road condition, and weather condition downstream of their current location. Thus, an acceleration modeling framework is suitable for this environment. Recently, intelligent driver model has been applied to model the connected vehicle environment. Since it has been improved to provide greater realism and reflect the operation of driving assistance systems. Thus, the connected vehicle behavior was regulated by external driver model in VISSIM, and it was developed with a C++ program. The value of the parameters in the IDM model was determined based on previous study. The IDM model is a nonlinear car-following model which specifies a following vehicle's acceleration as a continuous function of the vehicle's current speed, the ratio of the current spacing to the desired spacing, and differences between the leading and the following vehicle's velocities. This figure displays a flowchart of implementing the VSL controls in connected vehicle environment. On the freeways, a bottleneck could occur due to various reasons, including construction, crashes, etc. The traffic data collected at downstream, the current post speed limit, the visibility distance are used to calculate the safe speed for upstream vehicles approaching the congested segment, which is based on the equations that was mentioned in the previous slide. If the recommended speed limit is less than the initial speed limit, the process will be repeated until the bottleneck is not existed. Otherwise, the VSL control will stop. The post speed limit of the VSL will also be adjusted based on the relationship between the speed of real-time traffic and post speed limit at the current time step. All VSLs are determined especially from downstream congested segment to the upstream. The connected vehicle control could help overcome the limitation of VSL-only strategy that drivers would respond differently to the suggested speed. Besides, the connected vehicle technology could mitigate the adverse impact of fog by providing the following vehicle the location information of the leading vehicle. The variable speed limit information could be sent to all connected vehicles through the V2I communication. Thus, it is expected the connected vehicle technology could help provide more effective VSL control strategies to reduce rear-end crash risk in fog. On the other hand, the VSL control strategy could provide a safer driving environment for connected vehicles under the fog condition. This table summarizes the effect of the VSL control with various driver compliance rate compared with the base condition. 3 different compliance rates were tested that includes 30%, 60%, and 100% in the simulation. 2 different traffic conditions are tested, which include low volume and high volume. The results show that the VSL control could efficiently reduce the rear-end crash risk across the different VSL appliance rate, and the crash risk was decreased with the increase of VSL compliance rate. When the compliance rate grew to 100%, the VSL control could achieve the largest impact for the scenario of both low volume and high volume condition. The differences in crash risk under 3 different compliance rates confirm the conclusion that VSL's impact on safety varies by driver's compliance level. Compared with the scenario with high volume, the scenario with low volume could have better VSL control performance, which might be due to the severe traffic congestion. The left figure shows the reduction of time to collision by each detector when the compliance rate equals to 100% for low volume condition, which has the largest safety improvement. It is indicated that the VSL could consistently reduce the rear-end crash risk for most of the location at the upstream of the crash location. This table compares the effect of VSL only with 100% compliance rate connected vehicle and implementing VSL in a connected vehicle environment. Negative value of the change of time to collision or the change of total travel time indicates reduced crash risk or improved traffic efficiency. The results show that both VSL only and connected vehicle only control strategy could efficiently reduce the rear-end crash risk for both low volume and high volume conditions. In addition, the better performance of the VSL control could be found in connected vehicle environment, indicating that the advanced character of the V2I and V2V control system. When a safe speed limit is determined by the proposed VSL control algorithm, the information could be sent to all connected vehicles at the segment immediately, and all vehicles will follow the suggested speed timely. Also, connected vehicle could also diminish the increase of travel time caused by variable speed limit strategy, especially for high volume conditions. Based on the micro simulation experiment, we can find that compared with the vehicles without any strategy, the proposed VSL control strategy could effectively reduce the rear-end crash risk under full condition. The safety performance of the VSL is better with a higher driver compliance rate. When the compliance rate is 100%, the rear-end crash risk could reduce by about 30% and 6% for low and high volume conditions, respectively. The results demonstrate that connected vehicle could also improve traffic safety and traffic efficiency. Implementing a variable speed limit in a connected vehicle environment could further enhance traffic, while connected vehicle could diminish the increase in travel time caused by variable speed limit control. Thank you. Yeah, I would like to take questions.
Thank you very much, Yina.
Thank you.
Could you very quickly review for me, because I didn't quite catch it, how if the simulator results led into the micro simulation results? I know I asked about that a lot, but it's
Yeah, so actually there are two different like experiment, and like one is driving simulator experiment and one is micro simulation experiment, but they have something similar. Firstly, both of them are analysis the connected vehicle effect under fog condition, and both of them are focused on the rear-end crash risk. So that is actually there. So when we do the analysis, there's something that like the VSL control strategy, the equation, that they are something like connected in, yeah, but actually there are two different simulation experiments.
Yeah. Two independent.
Yeah.
Thank you, Yina. He says thanks.
Yeah, thank you.
Interesting mixed approach to sending micro simulation. What's the next step for this line of research?
Pardon? I cannot hear it clearly.
Let me try again.
Yeah. Yeah.
Bill says, thanks, Yina. An interesting approach to sim and microsim. What's the next step for this line of research?
Yeah. So in the current micro simulation scenario, we only consider the scenario with connected vehicle have 100 market penetration rate. So in the future study, we are going to test the connected vehicle with different market penetration rate and integrate it with the proposed VSL strategy to see the impact of market penetration rate. Yeah. So that is the plan for the macro simulations analysis.
Ilsa's great in response. Are there any other questions?
Thank you.
I don't see any coming up in the chat. But yeah, I'm sure people are welcome to contact you if they have questions in the future or they think of something. Thank you for sharing our presentation today. And thank you for everyone who attended. Thank you, everyone. And we'll see you next time.
See you. Thank you.